Okay, we're going to continue today with the derivatives of sine and cosine, which are the trig derivatives. So you have to memorize these two, that the derivative of sine is cosine, and the derivative of cosine is negative sine. This is just continuing from where we left off yesterday. So I'm going to start with the proof of just the derivative of sine. We'll do that proof. I won't go through the proof of the derivative of cosine, but it is similar. So let me start with using the formal definition. So limit, and I'll use the delta x definition as delta x approaches 0 of sine of x plus delta x minus sine of x all over delta x. And then what this is going to use, I'm going to use my addition formulas, right? So that just becomes the sine of x times the cosine of delta x plus sine of delta x cosine of x, and still minus sine of x all over delta x. And then we're going to split this up a little bit. So what I'm going to do is I'm going to split up the first part here. And we're going to just look at the limit as delta x approaches 0 of sine of x cosine delta x over delta x. Because for this, oh whoops, I split up the wrong part. I wanted to just split up this middle part. Sorry about that. So it's this middle part that I want to split up. Sine of delta x times cosine of x. Because why do I want that middle part? Because I know that the sine of delta x over delta x, as my delta x approaches 0, I can separate that one out, and that's going to just give me 1. And so this part just gives me 1. So I've got 1 times cosine of x for this part. Okay, and then plus, and then I can do these other parts here. I'll do the limit as delta x approaches 0. And so the other part that I have left is sine x cosine delta x minus sine x all over delta x. I can factor out, in this case I'm going to actually factor out a negative sign, and I'll show you why I factor out the negative sign, because then I'm left with 1 minus cosine delta x all over delta x. You can see where this is going, because now the limit as delta x approaches 0 of this part is just 0. And so I have negative sine x times 0, which is obviously just 0. So then bringing this down, I have 1 times cosine of x plus 0, which is just cosine of x. And that's your proof. That's where it comes from. Okay. Now you're not going to be asked to do that proof again, but just so you know where it comes from, that is the derivation of it. So let's work through these derivatives involving sine and cosine. So since the derivative of sine is cosine, all that I'm going to do is take 2 times and then sine. The derivative of sine is just cosine. And so my answer for y prime is just 2 cosine. So you can just multiply them together when there's a constant out front. This is the same thing. It's like 1/2 of sine, right? This is really 1/2 sine x. So really it's just 1/2 of cosine. And so my answer would just be cosine x over 2 for dy dx. And then for this one, similarly, I can just take the derivative using my sum and differences here, take the derivative of each one. So first take the derivative of x, which is just 1 using power rule. The derivative of cosine is just negative sine. And so therefore the derivative of the whole thing is just 1 minus sine x. So those are pretty easy. Okay, let's move on to the next page and talk about rates of change. So you've seen this whole thing, we can just read through this. You've seen how the derivative is used to determine slope. The derivative can also be used to determine the rate of change of one variable with respect to another. Rate of change and slope are very similarly related. They're not exactly the same though. Applications involving rates of change occurs in lots of different things in real life. Population growth, production rates, water flow rates, velocity, acceleration, a lot of things you've seen in physics. A common use is to describe the motion of an object moving in a straight line. The function s is sort of our displacement or position function relative to the origin of an object as a function of time, again, is called the position function. So s of t is our position function. If over a period of time delta t the object changes its position by amount of delta t, t plus delta t minus s of t, this recognizes, then average velocity is just the change in distance over change in time. And so this definition of average velocity. So let's find the average velocity of a falling object. If a billiard ball is dropped from a height of 100 feet, blah, 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 here's your function. That's your position function. S is feet, t is seconds. Find the average velocity over each of the following time intervals. So this part, pretty simple. All we're doing for average velocity is delta s over delta t. So delta s is just s of 2, plug in this number, minus s of 1 over delta t is just the change in time. Well, that's just 2 to 1, 2 minus 1, right? So what is s of 2? Well, I have to plug it into my function up here, right? So that's negative 16 times 2 squared plus 100 minus, and then I plug in a 1, negative 16 times 1 squared plus 100 all over 1. And so then when I work that out, blah, 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 it should simplify, I believe, use your calculators. You can figure it out to negative 48 feet per second. Velocity is always given as feet per second, miles per minute, whatever. It's a unit of distance divided by a unit of time. Similarly, here we would do the same thing. So I do s of 1.5 minus s of 1 over 1.5 minus 1. Change in s over change in t. And again, when I work that out after I plug everything in, you should get, I believe it's like 64 minus 84 over 0.5, which is about negative 40 feet per second. Notice these numbers are getting closer and closer to something. Delta s over delta t for this one would be s of 1.1 minus s of 1 over 1.1 minus 1. And again, when you use your calculator, you should get something like 80.64 minus 84 over 0.1, which is about negative 33.6 feet per second. What's happening here? This is a distance here, a time of 1 second, right? This is 0.5 seconds, this is 0.1 seconds. So we're getting closer and closer and closer to what I want, which is called an instantaneous velocity. So this next part talks about, supposing I wanted an instantaneous velocity right at 1. I want to know exactly at 1 second how fast is that object going. Now it's obviously going to be pretty close to these numbers here. Notice these are sort of converging to something. To do this, you need to take the limit as delta t approaches 0, right? And so I'm just going to use my limit formula here, which is the derivative. And so I would just use my derivative and work it out, and I would get my actual value on that one. So instantaneous velocity is just the derivative of your position function, okay? So memorize that. If ever I ask you for instantaneous velocity, all you're going to take is the derivative of the function at that value. And you can either do it the long way, or you can use your power rule and use it that way to find the derivative. Definition here, speed is the absolute value of velocity. So if you ever have a question involving speed, just take the absolute value and it would always be positive. Example 10, using the derivative to find velocity. So at time 0, a diver jumps from a platform 32 feet above water. The position function, here it is, s of t, where s is measured in feet, t is measured in seconds. When does the diver hit the water? Well, the diver hits the water when s equals 0. Because we're starting at 32 feet above water. Hitting the water would be a distance of 0, okay? And so all I'm going to do is plug in a 0, and I would solve this. Negative 16t squared plus 16t plus 32, which means I would factor, and I get t minus 2, t plus 1. So there's two answers, at time equals 2 or at time equals negative 1. Well, obviously we can't have a negative time, so my correct answer here would be at time t equals 2 seconds, is when the diver hits the water. What is the diver's velocity at impact? So this is what I want. I want instantaneous velocity at time equals 2, at that time that I just found. So what's instantaneous velocity? Well, instantaneous velocity is just the derivative of my position function. So let's use our power rule and find that derivative. So it's negative 16 times 2 t to the first plus 16 t to the 0 plus 0.
Oh, I'm sorry.
It's all right. I'm just recording. What's up?
She lost her calculator.
Okay.
She's a senior.
Okay. Thank you. I'll come find her. S of t then, when I multiply this out, negative 32t plus 16. Sorry about that. And now I want to find that at 2. So all I'm going to do is take this 2 and plug it in here. So s prime of 2 would just be negative 32 times 2 plus 16. And you get negative 48 feet per second. And that is the instantaneous velocity when the diver hits the water at time equals 2. And that's it for your notes.